I'm pleased to announce today's speaker, Yong-Tao Cui. So Yong-Tao obtained his BS from Peking University in 2005, and then his PhD from Cornell University in 2011. His PhD thesis work was on the study of spintronics in nanomagnets. And after that, he moved to Stanford University as a postdoc researcher. And there he worked on the development of microwave impedance microscopy and its applications to the study of electronic states in quantum materials. So he worked on that prior to joining UCR as an assistant professor, which was in 2016. So today he will talk to us more about this work on probing emergent electronic states in 2D quantum materials. So Yong-Tao.
All right, yeah, thank you, John, for the kind introduction. Can you guys hear me okay? Good, okay, great. Can you also see my screen? All right,
yes.
Okay, let me see. Change point. All right, okay. So it's a great pleasure to have this opportunity to report the research progress in the past 5 years in my research group since I started as an assistant professor at Riverside. So it has been a very challenging, but also very enjoyable 5 years. This is how my lab looked like when I first arrived. And as you can see, as time goes by, the entropy has been increasing. And also it went through a couple of phase transitions, and this is what it looks like now. Okay, so today I'm gonna talk to you about the research project we worked on in the last few years. They're mostly about 2D materials. But before that, let me first actually put up the most important slide of this talk. And I want to first thank all the students and postdocs, including graduate students, undergrad, and also a few visitors who have worked in the group and contributed to various research projects. And also want to thank all the collaborators, both within UCR and also from outside UCR and even outside of the US. And of course, all the funding sources who have supported my research. Okay, so first I want to give a brief overview of what we are working on before going into the details. So the research, the material systems that we're interested in are the so-called two-dimensional materials. And those materials are basically atomically thin layers of materials. As a famous example of this graphene, and that is basically a single layer of carbon atoms. And the reason we want to study this system is because, first of all, they're ideal 2D systems, because that's the thinnest possible thickness, down to the single atomic layers. So that's the simplest, the thinnest systems that you can get. So the electronic behaviors or the properties of the system is strictly in the 2 dimensions. And this property also allows make a lot of those 2D materials to exhibit like extreme physical properties. So for example, take the graphene as an example. It's mechanically it's actually even stronger than diamond, which we know is basically another form of carbon. And electrically, it's also more conductive than a very good conductor that we use a lot. That's the copper. And it's also the best thermal conductors. So the 2D systems has a lot of like interesting properties that we can explore. And since the discovery of graphene, there have been many other 2D materials that are being discovered. So for example, this transition metal dichalcogenate, we call them TMD. So there are actually multiple materials that are in this category. So they are also 2-dimensional materials, although strictly speaking, it's not like a single layer, but all these atoms, they're kind of like bonded strongly and within this kind of like a tri-layer structure. And another commonly used material, 2D material, is this hexagonal boron nitride. It's a structure very similar to graphene. And the atoms, we know that the boron and nitrogen are simply neighbors to the carbons in the periodic table. So they can form a honeycomb lattice similar to the graphene. And this, although it's not talked about a lot, but it's actually a very commonly used materials because it serves as a almost ideal two-dimensional substrates for other materials, 2D materials of interest. So now you actually will see this in almost every high quality 2D devices nowadays. And our research is primarily interested in the electronic properties of those 2D materials. And in that sense, we can say that the graphene is a two-dimensional conductors. And for those TMD materials, they're actually two-dimensional semiconductors. And the hexagonal boron nitride is an insulator. And there are a lot of other 2D materials that exhibit very novel like electronic properties. So for example, 2D superconductors, magnets, and also 2D topological insulators. So a lot of focus of our research is on this like a new kind of quantum states, and what kind of like new quantum states that we can discover in this new 2D materials. Okay, so in our lab, we studied those materials using a somewhat specialized technique. It's called a scanning probe microscope. So let me first give you a quick introduction and what this probe is, what this technique is. So it's actually, the idea is very simple. We want to probe the materials on the very small, like nanoscale, length scale. So then what we can do is we prepare like a very sharp tip. So it's kind of like a poke materials and then probe the materials response. And sometimes we just simply prepare like a sharp needle. And this needle is actually very sharp at the end. And the sharpness or the size of the apex of the tip is on the order of like 50 nanometers. That pretty much sets the spatial resolution of this kind of techniques. And then because the tip is very delicate, so we want to make sure that we can both preserve the tip and also preserve the sample. We don't want the tip to crash into the sample. So we sometimes use this kind of like more flexible probe. And this is a probe with a cantilever. And this cantilever is softer and it can bend when it's touching the sample. And then what you see here is that we position an optical fiber, and this is a side view. So basically, we position this optical fiber against this cantilever. So between the two surfaces, it simply formed optical interferometer. And we know that it is very sensitive to the length of this cavity. And that's what we use to detect the tiny deflection of this cantilever. From that, we can learn about the forces applied on this cantilever. Okay, so there are many kind of variations of this technique. And depending on the probe you choose, and depending on the kind of measurement you do with the probes. So in our lab, we focused on this microwave impedance microscopy. So in this case, we basically use a microwave signal. So that's an AC signal. And we use that to measure the little capacitors and the resistors that's formed between the tip and the sample. So that can tell us information about, say, the local conductivity of the sample. And normally when we measure the conductivity of a sample, we need two probes, like the multimeters. But in this case, we can do that with only a single probe. That actually has a lot of advantages in specific like experiments. In other cases, for example, we can use a magnetic tip, and then we can use that to sense the magnetic force that's produced by the spins in the material. And then we can probe the information such as the magnetic domains in the magnetic materials. In another case, we can also simply just apply the voltage across the sample and the probe, and that will induce some charges at the surfaces. And then we know positive and negative charges, they will attract each other. So that will apply a force on the sample, on the probe. And then from that, we can learn information about, say, the electric potentials. So in the last few years, we have applied all the different kind of techniques, primarily using this microwave impedance microscopy to study like a various 2D materials. So here is an overview of all the different projects we have worked on. They're kind of like grouped into 3 categories. The first group is this Murray superlattice. And that is a new periodic structure that can form when we stack multiple layers of 2D materials together. And we can study things like the geometric structures, like the dual Murray patterns, when we have 3 layers. And also we can study some of the novel electronic states that can emerge in some of those Murray superlattice. Another group is this 2-dimensional topological materials. So in those materials, what's interesting is this conducting edge states. And then we can study this in a few like new topological systems like this monolayer Tungsten Telluride, which is a quantum spin Hall insulator. And more recently, we have been studying this manganese bismuth telluride as a 2D chain insulator. And we have also studied like 2D magnetic materials using magnetic force microscopy to study the magnetic orders in 2 dimensions. Today we're going to focus on this Murray superlattice and also another case in this topological system. So I'm going to use those 2 examples as a case studies to kind of like give you some idea on how we apply the scanning probe technique to study like electronic states in 2 dimensions. Okay, so before going into details, let me first give you a simple introduction in terms of why we want to study electronic materials. And we know that the conduction properties or electrical properties of materials can be used to actually categorize different materials. We know that we have conductors, which can conduct electricity. On the other side, the insulators cannot conduct electricity at all. And then somewhere in the middle, there's semiconductors whose conduction property can be controlled. So from those different electronic materials, we can make functional elements, for example, resistors, capacitors, or like diodes or transistors. And then we have, been very good about making those components. And we know that these are pretty much the building blocks for modern technology. And the reason for the success is because we can understand the materials' electronic properties very well so that we can develop new materials and also develop new methods to manipulate and to control them and to use them as the way that we designed to perform like very advanced functions. And our understanding in terms of electronic properties from the perspective of condensed matter physics is actually based on a simple theory called the band theory. So we know that in the materials, there are a lot of electrons. And the electronic states of those electrons can be described in terms of their energy relation with respect to the momentum. So we use this K to indicate that their momentum. And then it turns out in crystals. And thus the band theory tells us that the energy states actually kind of aligned in the form of energy bands. That's a specific relation of energy with respect to momentum. And then when we put the electrons in the materials are simply fill up these bands. And then at the topmost, we have the conduction band and also valence band. In the case of conductor, we have a lot of free electrons. What that means is that the valence band is completely filled, while there are also extra electrons that will sit in the conduction band. And this, because this conduction band is only partially filled, that means there are a lot of empty states around. So the electrons can move around very easily. That's why the conductors can conduct electricity. On the other hand, for insulators, we know there are no free electrons. And in terms of the energy band, that means the valence band is completely filled, where there are no electrons at all in the conduction band. So then there are no mobile electrons that are able to carry electricity. And then the semiconductor is kind of like somewhere in between. It's actually similar to the case of insulator, except that the gap between the 2 bands is small. So what that means is that thermally you can excite, or from other means, you can excite some electrons to populate the conduction band. And then it will become conductive because now you have mobile electrons. And depends on the number of electrons that you can populate, then you can control the degree of conduction in the semiconductors. So this is how the band theory explains the different electrical properties in the different materials. And now, and it has worked very well in the last half a century also. So now if we want to look for new physics, we want to remind ourselves why the band theory works. Because in the cases where the band theory may fail, may provide some opportunities to look for new type of physics. So let me give you a kind of like a one slide refresher about why the band theory works. And then we know that the solid state systems are intrinsically a many-body system. So it has a huge number of electrons and ions. So if we want to solve this problem, this many-body problem, like exactly, we need to include all the terms from all those electrons and ions, and especially the interactions among all of them. So that makes it pretty much impossible to solve. But then there are a few nice features of this solid state system that make it easier. One feature is that the ions are actually arranged in a periodic lattice. And this means it's periodic in all dimensions. And as physicists, we all love periodic systems because we know that the eigensolutions to the wave function will be periodic. So that means if we take the eigenfunction and then move it over one period, we know it's going to be the same as the original wave function up to a phase factor. And in this phase factor, there's a wave vector. This k will be on the order of 2 pi over L, which the L is the length scale or is the periodicity of this lattice. Okay, so this takes care of the ions. And then for all the electrons, they're actually only weakly interacting in most materials. And this allows us to model the interactions between one of them, the one electrons with all the other electrons. And then we can model all the other electrons, kind of like an average, a background, kind of like an electron sea. And the effect of that is just to screen the ionic potentials. So that effectively reduces the problem into a single particle problem, which is now solvable. And of course, this depends on that the interactions are weak. So then you may ask, what is weak? What can be considered as a weak interaction? So in the normal case, this is the rule of thumb is that you can compare the kinetic energy with the Coulomb interactions. And if the kinetic energy is much greater than the Coulomb interactions, it can be considered as a weak interaction. So the idea is that if the electrons can move around very easily, so it can interact with many electrons. So then the average effect is kind of like an average effect. There's no specific electrons that this electron will interact like strongly. So that's considered as a criterion for weak interactions. And those are the important approximation for many solid state systems. And if this approximation fails, so meaning that if there are strong interactions, that actually can often lead to very novel quantum physics. So for example, a famous example is the high temperature superconductors. And also, this also opens up entirely like new field that's called a strongly correlated physics. This strong interaction, a lot of times is also referred to as strong correlation. And we're actually going to talk about some of the 2D systems that potentially fall into this category. Okay, so that brings me to those two case studies I'm going to talk about today. And the first is actually this Mori superlattice. And we're going to explore some of those correlated physics that can be enabled in this Mori superlattice. Okay, so first of all, what is Mori superlattice? That is actually a simple geometric effect. And that's just the interference patterns of two similar structures. So for example, here I have two honeycomb lattice. That's the same lattice as the graphene. And then those two lattice has slightly different size. So if we place one lattice on to the other, right? Okay, so somehow this animation, oh, okay, great. So as you can see that when I place it on top of the other, it actually forms a new periodic structure with a much larger periodicity. And this is a so-called the Mori pattern. And this Mori pattern is actually very sensitive to the angle alignment. If I rotate this lattice by just a couple of degrees, then you can see the periodicity changed. And if I rotate a little bit more, you can see the periodicity now shrink a lot. Right? So at the largest periodicity, it's the length scale is on the order of 10 nanometer, or sometimes even more on the order of 100 nanometers. So that allows us to use scanning probe techniques to image this Moray lattice. And in fact, in one of our recent work, we have used this microwave impedance microscopy, we call it MIM, to study the Moray lattice formed by graphene and boron nitride. So in this case, from their lattice parameters, we know the periodicity should be about 14 nanometers. And we can see that in this case, we actually achieve really high spatial resolution and down to about 1 to 2 nanometers. That's actually beyond the nominal values we talked about, which is like 50 nanometers. And there's actually a reason behind that. But I'm not gonna go into details, but just saying that this Moray lattice can exist if we can manipulate the 2D materials to a high precision. And the research interest in terms of the electronic states in the 2D Moray system has actually exploded in recent years. That's after when the superconductivity was discovered in the so-called magic angle twisted Billiography. What the system is you take two monolayers of graphene, and then you align them such that their twist angle is about a magic angle that's around 1.1 degrees. And in this case, people have found that there are superconductors, and also there are other cases like mod insulators. And the behavior actually mimics the properties of the high temperature superconductors. So people view this as a strongly correlated system, and that may help us to understand better why there's the mechanisms for the high temperature superconductors. And the reason for this strong correlation in the system is believed to be related to the formation of the so-called flat mini-bands at this magic angle. So according to a very early calculation, and if you align this two layers at the magic angle around 1.1 degree, and then you can form this very narrow band in this Moray system. And in this case, the correlation can be enhanced in this mini band, which is really flat. The flat means the width, the energy width of this band is very small. So that can be understood in this kind of like a simple picture to compare. Remember, we compare the kinetic energy with the Coulomb interaction. So in this case, the kinetic energy is p squared over 2m. And this momentum is related to the wave vector, the k, which is 1 over the periodicity. And then on the other hand, the Coulomb interaction, it goes like e squared over the distance. Again, it's on the order of the periodicity L. And then in this case, you can see that those two terms actually scales differently with L. The kinetic energy scales with 1 over L squared, and the Coulomb interaction only scales with 1 over L. So that means when L is large, this Coulomb interaction is going to dominate because the kinetic energy will decay faster than the 1 over L. And that is the case in the Moray lattice, because now the periodicity is no longer the atomic lattice size, but rather it's this periodicity of this Moray lattice, which is much larger than the atomic size. So that's why this the Coulomb interaction can dominate. But in this magic angle twisted Billiography, it's very sensitive to the angle. The reason is because, so as you can see that from the experiment, the superconductivity is only observed around the magic angle plus minus like 0.1 degree. So the reason is that the graphene itself does not have a band gap in itself. So then it really depends on the alignment and the interaction of the two sheets. And so that only happens around a very narrow range around this magic angle. Okay, later on, people realized that another kind of 2D materials, this TMD, the transition metal ditrichalcogenide, could be a better system to study in terms of the strong correlations. And these materials themselves are semiconductors. So that means we have a valence band and the conduction band. They're separated by energy gap. And then when we stack two of those together, and especially if you pick two different materials, say the tungsten sulfide and the tungsten selenide, they have a small lattice mismatch, about 4%. And then if you stack them even at 0 degrees, you will get a Murray superlattice with a periodicity about 8 nanometers. And then that's going to do something to the energy band. And because we know that when we have two periodic functions modulating each other, we're going to get beating patterns. So what that means is that you're going to get K1 plus K2 and also K1 minus K2. And in the band structure, what happens is basically this original band from the single layer tungsten selenide is going to shift it in both directions. And then it's going to create overlap in this so-called mini beryllium zone. And then at this crossing point, it's going to avoid this crossing so that a gap will open at every of those crossing points. So that eventually make the so-called the Murray mini band. So originally we have one band, and if you fold this band, you can get actually 3 bands. And if you notice, this first band is actually becomes much flatter, right, so compared to the original band. Okay, so that's the case for basically all the all the energy band involved in the system. Both the valence band and conduction band in both the tungsten diselenide and tungsten disulfide will be folded and created this multifold of the Murray mini bands. And the energy alignment of the 2 layers is such that if you dope the system to the whole side, it's going to only dope the first mini band in the tungsten diselenide. And if you dope it to the electron side, you're going to populate the electrons in the first mini band in the tungsten disulfide, which is a different layer. So, and then for our case, we're going to study the electronic properties when we fill this first band, which we know they're flat. So potentially they can have enhanced correlations or electron interactions. Okay, so let's think about how we fill electrons in this Murray superlattice. And then how their electronic properties will be based on what we know from the band theory. So first of all, if we leave the Murray superlattice empty, so that means there's no electrons on this Murray mini band, then corresponds to obviously insulating states because there are no electrons. And then if we fill this lattice, to the maximum possible occupancy, and that's basically 2 electrons per Murray lattice. Because of Pauli exclusion principle, we can have 1 spin up and 1 spin down, and that's the maximum occupancy. And then corresponds to basically filling 2 electrons on this Murray mini band. In this case, this Murray mini band will be completely filled. And in that case, it will also be insulating states. Okay, and then everywhere in between, it has to be conductive, because if you only partially fill this lattice, then electrons, there are a lot of empty states nearby, so electrons can move freely. So anywhere in between will be conductive, and that's what we know from the simple band theory. Well, but because potentially the electron interaction can be strong in this case, so that means the simple band theory can fail. So then let's say what a special case, that's the, we fill this lattice with just 1 electron per unit cell. And that means the band is 50% filled or half filled. So originally we would expect it's a conductive states because there's still empty states in the nearby unit cell. So electrons can simply just move around through this empty states. But now if we increase the electron interactions, and then we know that electrons have negative charges, they will repel each other. So then they actually prefer to stay at a distance away. So this is kind of like imposing a social distancing of all the electrons. So then when 2 electrons are nearby each other, they become rather unhappy, right? So they will repel each other. So that will cost additional energy if you want to put 2 electrons within the same unit cell. So therefore, they'd rather stay at the nearest neighbors. And so that actually become a stable state. And all the electrons are locked in their unit cells, so they cannot move around. So that become an insulator at this half filling. Okay, so that's already beyond the understanding of the conventional band theory. And then experimentally, there have been a few works reporting the insulating states that appearing at a half filling of this band. So they're all worked on in the system of tungsten diselenide on tungsten disulfide on tungsten diselenide. You use a transport or optics technique, and they found that there's insulating states appearing at a filling factor of 1 on the whole site. There are also a few other reports on other similar systems of this TMD Moray system. And then in one of the work, in addition to this one filling, they also found that there are two like new insulating states at this 1/3 and 2/3 filling of the Moray lattice. So what are those states? Okay, again, let's consider this filling pattern in this Moray lattice. And what if we enhance the electron interaction? So meaning that now our social distancing policy is enhanced. So instead of keeping, say, like 6 feet away, we want to keep the electrons at 10 feet away. So then that means, let's say if one electron occupies this lattice, we have to leave all the nearest neighbors empty. And then the next electron have to go to the second nearest neighbor, which is over here. Right? So in order to comply with these enhanced social distancing. If you do that for all the electrons, so they can form a pattern like this. And again, it's a triangular lattice, a periodic structure. And if we calculate the average occupancy of the states, it basically comes to about 1/3, exactly 1/3. And this also form a stable states. The electrons are locked to every other unit cell. And then that gives us the insulating states at a 1/3 filling. And then if this state is a stable state, the 2/3 state should also be a stable state. That's just because you can simply exchange the occupied and the emptied lattice. So you can get another stable states, insulating states at a 2/3 filling.
Hey, Yong-Tao, can I ask you a question?
Sure.
How come you don't see that in the resistance?
In the resistance, you mean in the previous data?
Yeah, I mean, you saw it in the optical, but
Right. So I think this depends on the quality of the sample. So I think in their initial samples in the transport, you don't see that. But I'm gonna present our data, which do show the signatures in the resistance for that.
okay.
Right. Okay. So we have 1/3, we have 2/3. Before moving to the experiment data, let's also consider another case. Let's say if we further enhance the social distancing. Right. So now, not only the nearest neighbors are not forbidden, the second nearest neighbor also forbidden. Then the next available electron has to go here and there. Right. So in this case, we can calculate the average occupancy that's at a 1/4 filling, and also 3/4 of filling. So they are symmetric. So those are the states that were not seen in the previous measurements. Okay, so now let's look at our measurement. So this work is a collaboration with Sufei Shi at RPI. So their group, they make this kind of like complex device structure of this WS2 and WSE2. And you can see that there's a piece of WS2 and also there's the right piece of WSE2. And from their shape, you can tell that they're aligned pretty close to a 0-degree alignment. And then they put this on a piece of graphite, which we can use to induce electrons in the system. And then in our measurement, and what we do is we can bring our probe in over this overlap region. So that's where we expect there is a Moray superlattice. And then we measure the local conductivity as function of the gate. And what the gate does is simply just induce carriers and put carriers on onto the system. Yeah, so okay, so there's a question here. Should we see peaks which corresponds to the average occupancy of 1 + 1/4 and 1 + 1/3? It's not the average occupancy, but it can be seen at, for example, 1 + 1/3. So that is 4/3. And that's basically because the Moray lattice, you first put 1 electrons everywhere. And then on top of that, you can put 1 electron every 3 unit cells. So that should also be a stable state. Okay, so come back to our data. So we are measuring the conductivity. So you can interpret this signal as the local conductivity. So whenever you see there's a dip there, we know that corresponds to a locally insulating behavior because it's a low conductivity. And then in this case, we tune our gate both to the negative side that will induce holes, and also positive side that will induce electrons in the system. And we actually see there are actually a bunch of those dips. And then we can calculate what are those in terms of the occupancy, the fraction occupancy. It turns out it's a series of simple fractions. So for example, there's 1/3, 2/3, and also integer 1. Right, so we see, first of all, we see this fraction, this insulating states on both sides of doping, while previous measurements only see it on the whole side. Okay, then let's take a closer look. So we basically zoom in this both the whole doping side and also the electron doping side, and we change the temperature slightly so that actually we can resolve some of the fine features better at a slightly higher temperature. So we can see that there's a 1/3, 2/3, and also 1, right? So those are what we expected. And also there's a 1/4. So next to this, you see there's a little dip here. That's a 1/4 filling. And similarly on the other side, you see this 3/4. And that's on the whole side. On the electron side, the filling, the patterns are similar, but there are 2 extra peaks. There's also a 1/6 and also 5/6. Oh, no, there's also another peak. That's also a very pronounced peak. That's exactly at the half, 1/2. So on both the electron side and the whole side. So that means in addition to this 1/3, 1/4 filling, we also see this new states of 1/2 and also 1/6. Right. So what are those states? What are the occupation patterns in the real space? Well, so then let's analyze this case. For the 1/2, that means we fill it to 50%. So that means we put it every other unit cells. So a simple pattern to do that is simply just fill the rows of those lattice every other row, right? So that will make sure that the average occupancy is precisely 50%. So that's basically a stripe pattern. And also this case, the interaction is going to be anisotropic because this electron is closer to the ones on the right, left and the right, but further away from the ones up and the top and bottom. For the one, yes.
There's a question, I think, on the chat from Alec.
Oh, yes. Yes, I talked about this, I think, earlier about this 1/4 plus 1/3. So basically, if you fill 1 entirely, and then on top of that, you can put a second electrons into the cells every 3 cells, right? So similarly, there's also 1 plus 1/4, right? So that will be 5/4, but it's not going to be the average filling because that average filling will be somewhere actually less than 1, right? So it may not be a stable case. All right, okay. For this 1/6, it's also can be realized in this stripe pattern. So basically, this 1 electron is separated like 2 cells along this direction, and then 3 cells along that direction. So on average, 1 electron occupy 6 cells. So that gives us this 1/6 filling. And of course, all those patterns that we have talked about, they're kind of somewhat like out of imagination, right? So it's kind of like an educated guess. So in our work, we also did some simulation to actually calculate and confirm that those arrangements are the low energy states. In this case, we collaborated with D. Xiao, who did some Monte Carlo simulation. So basically, you just create like random fillings of this triangular lattice, and then you can calculate the total energy and find the lowest energy. So indeed, for this 1/3 filling, the pattern is the same as we have analyzed previously. So basically, it's the second nearest neighbor. And then for the 1/4, we have the third nearest neighbors. That's consistent with our analysis. And in both cases, they're all in this case of triangular lattice. So in the case of a 1/2, and these also are the stripe patterns. But because when you fill the stripes, they're actually, because of the symmetry of the lattice, there are 3 alternative directions that are equivalent. So that's why in the simulation, you will see that the domains of the stripes, they're along all the 3 equivalent directions. Same thing for the 1/6. There are a lot of domains. So meaning that when you have a lot of domains, they could mean that the state is not that stable. So to check the robustness of those states, what we can do is we can raise the temperature in the system and then see at what temperature those states will disappear. In this case, you can see that all those fine features, they kind of disappear somewhere around like 20 to 30 Kelvin, and some of the features actually persist to about 40K. And above that, all the fine features are gone. But this integer filling actually goes all the way up to about 120 and even 160. You can see some signs of that. Right? So that means in this case, the interaction is really strong because the energy scale is on the order of 120K for this integer filling. But the other fractional fillings disappeared around 40K. And that also is quite consistent with the simulation results from the Monte Carlo simulation. All right, okay. So that's our experiment results in terms of this fractional filling states. So last year, there were also other groups have been also working on this. The few other works using optical techniques. So they also discovered all the bunch of like fractional fillings. There's also work from Joshua Lewis' group. So he used the photoluminescence to also discovered a lot of like fillings, like a very complex fractions. There's also work from Fuang's group at Berkeley. So they used STM to actually directly confirm that this filling pattern, this triangular filling pattern, and also the stripe phase are actually indeed the case in the system. So that's was really nice to see. All right, okay.
Yong-Tao, can I ask a quick question?
Sure.
Do you actually independently measure density through Hall, or this is based on some?
Okay, so okay, let me come back here. So there are two ways to measure the density. I mean, there's one way to not measure density but calculate the density. That is basically we can calculate the density assuming there's a parallel plate capacitor model. So use that, we can calculate the density of the in terms of the actual density we put on the Murray lattice. And then in order to calculate the fraction, we also need to know the size of the Murray lattice. And that's something we can measure using optical measurements to determine the alignment angle of the two lattices. And from that, we can calculate the density. So that's basically one way to confirm that the density. And then because in the feature, I mean, all the samples, the features are really pronounced, especially those integer filling features. So we can actually, actually, this is a lot of the case that we actually assign this, we assume this feature is the integer filling. And then from that, we calculate what will be the fraction, the filling densities at other features. And that also corresponds very nicely in terms of simple fractions. All right, okay. So as a summary, and also to talk about the implications of this Murray superlattice. So we believe that this actually offers a new platform to study this correlated physics. The reason that is that from our experiment, we can see that interaction strength is really strong, above 100K. And also it's long range. The interaction, the electron separated by like a third nearest neighbor or like a fourth nearest neighbor, they're still interacting strongly. So that's basically says the interaction strength in the system is really strong. And also the system is also very flexible and tunable. Compare that to the Murray, the twisted barrier case. Remember in the twisted barrier case, there's a magic angle is required. But in this case, in the TMD Murray, this is not required because by choosing the different TMD materials, there will be a lattice mismatch, so that the Murray pattern is formed due to the lattice mismatch instead of the twist angle. And also there are more choices for the TMD materials, so that we can combine different materials to form like different Murray superlattice combinations, and then provide a knob potentially to tune the correlation strengths. There's also another perspective that is the system is also possible to realize other kind of like novel quantum physics. The recent experiments are reporting signature of topological phase in this TMD Murray lattice, and also excitonic insulators. We actually have also been working on this, and we're actually writing up a manuscript we are just about to submit on this topic. And of course, there's always this question about whether we can find the superconductors in this Murray lattice given this strong correlation strengths. All right, okay. So now I'm gonna switch gear a little bit and switch to the second system, which is about 2D topological systems. And I want to talk about this in terms of how we can think of the electronic properties in a global sense versus a local perspective. Okay, so let me first give an introduction about topology. This again is a geometric concept. So according to Wikipedia, it says topology is concerned with properties that are preserved under continuous deformation. Right? So example is this Mobius strip. And then we know that the topological property of this is that it only has one surface. Right? So no matter how you toss this around, there's always one surface. That's this topological property, as long as you don't cut it. Right? So that means it's continuous deformation instead of like damaging the system. Another like popular example, which we probably have seen a lot, is this donut versus this coffee mug. So they belong to the same topological category because they only have one hole in the material, in the body. So that means under smooth deformation, you can convert this coffee mug smoothly into a donut shape without breaking the material. Because their topological property belongs to the same class. Okay, so how do we apply this concept to condensed matter systems? So again, we can analyze in terms of band properties. And we can define a topological order in terms of the orbital characters, because we know the orbitals can have like S, P, D, F. And typically the D orbitals will have a higher energy than the P orbitals. So that means the conduction band will be of like D orbital, the valence band will be like P orbital. That's the normal case, normal insulator. But if somehow there's additional interaction, for example, very strong spin orbit coupling, so that can raise the energy of the P orbitals. So now the P orbital sits at a higher energy, it becomes the conduction band, and the valence band is the D orbital. So in this case, the topological order in terms of the order of the orbitals in the energy bands, they're inverted compared to a normal insulator. In this case, we can define this as a topological insulator. So although those two band structures look similar, but remember, they cannot transform from one into the other without breaking things. So that means if we create an interface and put those two materials together, something has to happen at the interface. And that is basically the closing of the energy gap and then reopening of the energy gap. So what that means is that at the interface, the energy gap has to be closed. So that means there are going to be gapless boundary states. And the existence of this boundary states is not because of something special about the interface, but because the interface is the boundary between the two topological orders that are defined within each domain. So it's a global order defined within each domain. But then at the boundary, something has to happen because of that global order. Okay, so to make it a more like intuitive, I'm gonna make an analogy in terms of a traffic system. So we know that in the US, we drive on the right-hand side of the road. So that's our traffic pattern. And then in places like UK, people drive on the left-hand side of the road. Right? So those different traffic system can be considered as topological orders. So now if we want to interface those two systems, so imagine if we want to build a highway bridge connecting US and the UK, all the way across the Atlantic. So how do I make sure that the traffic on the US side drives on the right-hand side of the road, but it switch to the left-hand side of the road as it enters the UK? So we have to build like an overpass somewhere in the Atlantic. And then we choose the location to build this overpass. It's not because of something special about this location, but because it separates this two traffic system exactly. No matter where you pick it, it's going to separate this the two traffic system or the two topological orders. And of course, we don't really need to worry about building such a bridge, but somewhere else in the world, people do need. So this is the southern part of China. So in Hong Kong and Macau, people use the left-handed traffic system. But in mainland China, people drive on the right-hand side of the road. So when they build this bridge connecting Hong Kong, Macau, and Zhuhai, so they have to consider this. So one of the proposal is exactly this overpass that we have talked about. But I don't believe this is the final winner of the design. But I do find there's another bridge connecting Macau and Zhuhai. So this is what it looks like. And there has to be an overpass, although it's not so obvious, but it has to happen in order to define this, to separate this topological order. So you probably have found that it's actually happening over here, right? So again, it's not because something is special about this location. It's because this is the boundary between the two topological systems. Okay, so now coming back to 2D topological systems. And then what that means is that you're gonna get gapless states at the boundary of 2D system, which now becomes a one-dimensional edge. So that's the edge of the sample. So in 2D system, there's three like very famous topological systems. The quantum Hall effect, quantum spin Hall effect, and quantum anomalous Hall effect. The difference is that the spin configurations of this edge states. So for example, in the quantum Hall, both spin up and spin down, they move in the same chirality, same direction. But in quantum spin Hall, the spin up and spin down, they move in opposite directions. And then in the quantum anomalous Hall case, there's only one species of spin left. Okay, so and then the existence of this well-defined edge states can lead to some signature in the transport. For example, the famous example is the quantization of the resistance in the quantum Hall case. In this case, when you measure the Hall transport, and then the Hall resistance actually quantized precisely to this value defined by fundamental constant h/e². And because it involves the Planck constant, we know that it's a quantum effect. But the robustness of this precision, that comes from the robustness of the topological orders. And those topological orders, basically, the signatures of that is that you're gonna have gapless edge state, and also you're gonna have a topological gap in the bulk of the system, right? So those are the 2D, two key elements for topological order in the system. Okay, so then next I'm gonna talk about a couple of examples and how we use scanning probe techniques to detect these two signatures in some of the new 2D topological systems. Okay, so the first example is a monolayer tungsten telluride. And this materials has been demonstrated to be a quantum spin Hall system. So here is a picture of that, of this monolayer tungsten telluride. That's this stripe here. And then what's on top is a boron nitride. So that's basically protecting this material from oxidation. And then we can use our microwave impedance microscope to probe the local conductivity. And what we expect is that around the edges, it has to be conductive, while inside the bulk, it has to be insulating. So that's exactly what we see. And we can actually move around the sample. And no matter what the shape of the edge looks like, they're always like bright, meaning that they're highly conductive. And then you can see that this conduction is very localized at the edge. And this is the map of the entire sample. You can see that there's always, the edge is always conductive. And here's another example of this material. And in this case, this tungsten telluride is actually only partially covered by the hexagonal boron nitride. So that means this corner is actually exposed. So that becomes a trivial topological, in terms of topological property. And then this bottom side is still a topologically non-trivial part. So then at the boundary of this trivial and non-trivial region, and that's basically the edge of this boron nitride. So that's where we see this conduction states appear, right? So that's basically exactly as what we expected. They appear at the boundary of topologically non-trivial and topologically trivial regions. Okay, so that's the example in terms of tungsten telluride. And then I'm gonna talk about the recent work in this new system called manganese bismuth telluride. So that is a magnetic topological insulator. So in the sense that it actually combines both topology and magnetism in one system. And in this case, you can think of this as the crystal structure. You can think of this as a bismuth telluride, which we know is a topological insulator. And then you insert a manganese telluride in the middle. And then this manganese atom will carry a spin moment. And that's what producing this magnetism. And then when you stack these layers together, the magnetic moments are anti-aligned, so they form the so-called layered antiferromagnet. So they're aligned within the plane, but opposite in adjacent planes. So then theory predicts that the topological property of the system actually depends on the configuration of the magnetic states. For example, in all system, in all the layers, and you have this layered antiferromagnet, so up, down. Because if the total layers are odd, then you're always going to have a net moment. And the theory predicts that this should be a topologically non-trivial case. That's described by a chain number that's equal to 1. On the other hand, for the even system, we expect that there's no net moment, so the chain number has to be 0. And if we drive the system into the ferromagnetic case, then the odd even becomes the same because they all have the magnetic moment with a non-trivial topological character. So in the last couple of years, there have been a lot of experimental work trying to probe the topological properties in all the different magnetic configurations. I mean, although some of the results are published in like top tier journals, actually the results are actually still highly controversial at the moment. Okay, so in our experiment, we want to examine the topological properties and correlate it with magnetic states. This is a collaboration with several groups around the US. And this is one example of device. In this case, it actually has an odd layer on one side and an even layer on the other side. So we can probe both odd and even within the same device. So first, we actually characterize the magnetic properties using an optic technique called RMCD. So in this case, the signal basically is proportional to the moment, the size of the moment. And then you can see that at the low field, it has a net moment. So that's the consistent with this layered antiferromagnet. And then in the intermediate case, it converts into a so-called canted antiferromagnet. So they're not like perfectly parallel or anti-parallel, but they kind of a point like canted. And then when you further enhance the field, they're rotated towards the field direction. So eventually at a high enough field, everything is polarized in the same direction. So that's the same case in the even layer numbers. It goes through this AFM, canted AFM, and eventually to the FM. Then we can characterize the topological properties by doing Hall transport. And what we found is that this high field, the Hall resistance are like nicely quantized. So that indicates a non-trivial chain number and high field in the FM phase. But in the AFM phase, actually both give a very small Hall resistance that indicate a trivial case. So that means in this, there's gonna be a topological phase transition between the topological phase with different characters. In the this trivial or this C equal to 0 phase, we don't expect any edge conduction. But in this topologically non-trivial case, we do expect that there are going to be edge states. Okay, so that's the first thing we can characterize. So we can measure the sample, we focus on this edge region, and then we can tune the system into the quantized states, and we can scan a spatial map. And as you can see that when we tune it into the quantized states, we do see this nice edge conduction that's standing out. And if we further tune it into this highly doped region, then the system becomes conductive again everywhere. So that first confirms that we do see the edge conduction in this. This is, by the way, this is at 9 Tesla, so it's in the topologically non-trivial case. Okay, and then the second signature we're looking for is that if you go from the topological character of say C equal to 0 to a different topological states, something dramatic has to happen, right? So in the case of condensed matter system, that means the bulk gap has to close and then reopen. So that means there has to be a band crossing and inversion process. Then let's say how we can probe that. So in this case, we bring our tip to the middle of the sample, and then we only measure the local conductivity. So that indicates the local property of the sample inside the bulk. And then we tune the gate. At the same time, we tune this the magnetic field to drive it from the antiferromagnet to a ferromagnetic case. And we see a map like this. And then we can do alternative measurement purely using transport. And we can design the least configuration such that we only measure the conductions through the bulk. We get a map like this. So they're actually very similar to each other. So that confirms that both the MM and the resistance, the transport, we're measuring only the local, the bulk property. And then we can correlate this with the the topological characters that we probed using the Hall transport. And we found this is the region that the C equals to, in this case, C equals to -1. And then at the low field region, we have the C equal to 0. Okay, so then let me try to explain what happens when we go from the C equal to 0 to C equals to 1. So first of all, we see that there's actually a conductive feature that's appearing in this range. So we believe that this corresponds to that band crossing feature. So at higher doping, we have the system in the conduction band, and at the lower doping, the Fermi level is in the valence band. And then basically at a zero field case or low field case, there's an insulating states in between separating the valence band and conduction band. So that's what we expect for a trivial insulator. And then as I go to the canted AFM case, and then we see there's some feature, a conductive feature, that splits off from the valence, the conduction band. And then as the field further increases, this feature moves toward the valence band. So that means this kind of like this band split off, and then it moves toward the valence band. Eventually, at a high enough magnetic field in the ferromagnetic case, this band crosses all the way the band gap, and then it merges with the valence band. So that's the origin of this band inversion or band crossing. So that's producing the non-trivial topological character in the ferromagnetic states. And we believe that the motion of this, because it couples with the canting of the FM moment. So that means it most likely couples with the Z component of the magnetic moment. And when we drive it into the ferromagnetic case, we increase the Z component. So that moves the band down, and eventually it crosses, induces this topological phase transition. Okay, so this is also the same case in the odd layers. So we see the non-trivial region and trivial region and a very clear band crossing in between. Okay, so as a summary, we have used this local scanning probe method to probe the signatures of the topological phase transition. That is in terms of the conductive edge states and also the band crossing that induce the topological gap. So basically, we're using a local measurement to infer properties of this global topological order. And what we find in this material is that in actually both the odd layer and the even layers, they both go from a trivial case at a low field to topologically non-trivial phase at a high field. Okay, so that's the conclusion for the second part. So now that brings me to a quick outlook about this the 2D materials that we're working on. So we believe that this materials actually offer a rich platform to explore a lot of the new quantum states. And why is because people have been continuously discovering like new type of materials in this 2D material family. So that gave us the opportunity to actually create a multi-layer structure or heterostructures using all the combination of materials. So this is a figure I took from Nathan's perspective feature paper talking about the heterostructures. And then we have been developing like new capability to actually precisely manipulate their structures, potentially down to the atomic precision. So in a lot of sense, this is like playing around with Legos, right? So, and I think that the field is still at a very young stage, and it literally is probably at the age of playing around with Legos. And I believe there are a lot of potentials to build more complex structures. And of course, in that process, we need to develop like novel characterization techniques to probe those new states. And I hope that from my talk today, I gave you a little bit of flavor that what we do and how we can use this to investigate a new type of electronic states based on the 2D materials. Okay, so with that, I would like to conclude my talk. And here is the most important slide again. And I would like to thank you for your attention. I'll be happy to take questions.
Thanks, Yong-Tao. So, questions?
Can I have one?
Sure.
Yeah. Very nice talk, Yong-Tao. So in the flat minute bands part,
okay.
Because of the flat band and very often in solids that can lead to stoner instability. Is there any sign in your experiment or anybody's of ferromagnetism in such a system?
Oh, yes. Actually, the half-field band. Okay, actually, let me see if I can go back. Oh, okay. Let me go back and then let me share the screen again. Right, so in the half-field case, there has been experiments showing this while the details is not exactly clear. Okay, let me share the screen again. So basically, in this half-field case, there has been experiments showing that there's a magnetic order. Although some people say it's an antiferromagnet, but it may also be a ferromagnet. So this is, I think that has been experimentally reported. That's also actually potentially related to the topological phase. There's a follow-up from the Cornell group that actually demonstrated the quantum Nahm's in this TMD Moray system. That's actually also something that we have been working on. So I think the magnetism and the non-trivial topological property, they're probably connected.
Another short one. So since you have a two-layer, right? So two layers for forming Moray pattern. So where do those electrons live? Does it make any sense to think, they don't belong to any single one, right? Just
well, I think in this case, because of the band alignment, they actually live in individual layers. I think in this case, you can think of it like this. So let's first take a step back. Think about the graphene and HBN. Right, so we know that in that case, when you have the graphene and HBN Moray lattice, the electrons still live in the graphene because HBN is the insulator. What the HBN does is to impose this Moray potential on the graphene that form this Moray bands. Okay, and then in the case of this tungsten diselenide and tungsten sulfide, because energetically their bands are like separated pretty far away. So then if we dope the system, and then, for example, onto the whole side, and then the electrons will live only in the WSE2 layer. And then the role of the WS2 layer in this case is just to provide a periodic potential for the WSE2 layer to form this Moray mini-bands. And if you go to the other direction, so when you dope electrons in the system, then the electron actually live in the WS2 because of this band alignment. And then in that case, WSE2 will act now like this Moray modulator, like provides this Moray potential. So that's how we think of this where electron lives in this case. And of course, if you go to high doping, you can potentially fill both the WS2 band and also the WSE2 band. Yeah, so that's the I think that's the configuration. Right? So basically, one layer serves as this. One layer modulates the other layer, and the electrons usually only live in one layer, not at the interface or not at both. So that's somewhat different from the twisted barrier graphene case, because there it depends on the hybridization of the two layers. So the electronic wave function is kind of like a superposition of the two layers. But in this case, it's actually different.
Yong-Tao, can I ask a related question?
Sure.
If you go to really low densities, you could get the Wigner crystal. Do you ever see it?
Oh, actually,
some incommensurate distribution. This is all very commensurate, right? So do you ever...
Right. So we think that in this case, because there's already a background modulation due to the Moray densities, during the Moray potentials or Moray lattice, we actually call this a generalized Wigner crystal, because that's basically a Wigner crystal in the background of the modulating potentials. Okay, so in terms of the actual Wigner crystals without any modulations, people have observed that in just a monolayer of TMD, although I think the experimental evidence is still have a question mark. And also there's a bilayer of TMD, you separate them with a thin HBN. So in that case, there are no Moray lattice involved. Then at a very low density, it's basically purely due to the electronic Coulomb interactions. They can form so-called the Wigner crystals, but I think there's some initial signatures in experiments, but I think it's not conclusive yet.
So how low in density have you gone? Like you step, like how do you?
Well, so we can go all the way to, to very small density, but we don't see those, right? So we see, like we basically tune it all the way across
okay,
the gap,
not,
right? So
okay.
yeah, so, well, the other thing is, well, in those systems, if it's a Wegener crystal, right, at low density, that means it's independent of the actual dopings, right? So that means
it
the
should
spectrum
be, below some density, you should see
right,
it.
should be a continuous. So that means actually in the experiment, there's probably no good way to tell if you see like a continuous spectrum of insulating states. There's no good way to tell, it's close to a band insulator, but the low doping, right? So it's hard to tell if that's a Wegener crystal or.
No, but if it's anything incommensurate, the sort of,
right. So it's then continuous. We just see it's like, insulating states. There's no, like, in this case, like at the commensurate fractions, you will see like very distinct pictures.
Yeah.
Okay. But that's a good question. I think that's also a direction that potentially that we can explore in those TMD systems.
Yong-Tao had a question. A lot of times strong correlations lead to strong frequency dependencies, that are brought on by renormalized parameters, reduced parameters. Okay. I don't know how high in frequency you're going, but I mean, have you seen any evidence of that? I mean, do you think the transport you're measuring is identical to the DC transport?
Right. So I think at the gigahertz regime, it's still at a pretty low. Because one way to think about it is the wavelengths. Because at a DC, at a gigahertz, the wavelength is about like 1 foot, like 1 gigahertz in air. The wavelength is pretty long. So I think if there's any, say, we form the Maury lattice, there may be like a local, for example, vibrations or like a resonance on that length scale. That will be on a different, I think, probably a pretty high frequency.
Well, if I remember right, 5 gigahertz is about a Kelvin.
1 gigahertz, I remember, 1 gigahertz is 4 microvolt, right? So 5 gigahertz, so that level, but I
35 gigahertz is a degree.
Right. Okay, right. Yeah. So yeah, but in this case, like, I think what we're probing is like the, our frequency usually up to about 10 gigahertz. So that's still pretty low in terms of the temperature scale, energy scales. So probably hard to hit that resonance. And if you go above that, that's usually in the terahertz regime. And then it's not actually an electronics problem. It's more like an optics problem. So the approach may be different.
Yeah, that's right. Never mind.
Yeah, but actually in this Maury system, in the Wegener crystals, in this, like say, 2-deck based Wegener crystals, people has regard this microwave frequency response as a signature of that Wegener crystal, because when the electrons are localized, they kind of like locally, they form like local vibrations, and that frequency mode is in the gigahertz regime. But I think in our case, we don't have any signature of that yet.
Yeah. How high in frequency you go?
We can go to about like 15 gigahertz.
50, okay.
15, 15. Okay. Yeah, above 20, I think Igor knows the electronics, the cost of the electronics kind of like exponential.
Oh, I know that.
Okay. Yeah.
Okay. Thanks.
Yong-Tao, how good is your quantization of conductance from the edge at whatever temperature you measure? Are you almost at full quantization or no?
You mean in this manganese bismuth telluride?
Yeah, at the edge, yeah.
Yeah, so that's actually a pretty good quantization, and at like a 4K. Yeah, so better than. Well, actually,
you had the plot. I just wanted to look at it.
I have the plot, and then that there's okay. Let me quickly go there. We plot a contour that's, I think, 98% quantization.
Okay. Is that 4 Kelvin?
4 Kelvin, yes. Probably slightly below 4. We pump it a little bit. Yeah, over here. Yeah. So this contour is 98% H over E squared. And actually, at the best case, it's more, I think it's better than 99%.
And what's your bulk gap?
Okay, that's a good question. It's not very clear yet because this
Okay.
is a thin layers. There are past measurements in the box systems. That's also kind of like anywhere between like 20 to like 50 millivolts. So I think maybe even higher, but I think it's not reliable yet.
Okay.
Okay, one more question, Harry.
Yeah. Can you describe the polarization of the microwave probe?
Oh,
I mean, are you
we're in the near
coupling
field
to
regime.
vertical electric field?
No, in this case, we're in the near field regime, and then so the polarization is now well defined. A simple way to think about it is just it's a tip, so it has a sharp geometry, and then at the tip there's all this the fringing field from the tip. So that's
I
like
see.
yeah.
Yeah.
So that's not a well defined like a EM mode. So
you
that's
can get
unfortunate.
you can get parallel as well as perpendicular.
Right. So basically, it's not well defined. That's something that we don't have a good solution. Because otherwise it can potentially probe for example, the magnetic states or even the some other, the directional kind of anisotropy of the system. Yeah.
Right. So does anybody think of fabricating the tip on a finer scale?
Yeah, it's
in a way to do
quite
that.
challenging. So for example, you can probe two tips, like the electric field will be like in between the two. Yeah. So I mean, I don't think. I mean, even okay. So now talking about the microwaves, just there are a lot of people working on so-called the multi-probe scanning probe, just to make multiple probes. It itself is a pretty like big challenge. There's no good progress in that direction yet. So if people can do that, then we can think about how to put up, because you need to put a positive voltage on one side, negative voltage on the other side, right? So yeah, so that's quite a challenge, I would say, at this stage.
Okay, thanks.
Yeah.
Okay. Thank you, Yong-Tao. That was great.
Yeah, thank you.
Thanks, everyone.
Yeah, thank you.